Good afternoon. Welcome to South Edge University 2023. In this session, we're going to take a look at South Edge simulation. We're going to take a look at what's new that was offered in the South Edge 2023, as well as some interesting topics from previous versions, of course. The first focus would be on assembly body mesh. That feature allows for better mesh creation automatically, and it's now available not only on parts but also in assembly and the sheet metal environments. Then we're going to talk about reuse of mesh. It's very important when you copy or duplicate study to be able to do it in most efficient way so you can go through what if scenarios. And this is exactly what it's aimed at to make sure that you can reuse mesh from previous study automatically. We're going to take a look at new mesh quality check. It's very important to understand how good your mesh is because the accuracy of your results depend on mesh quality as well. And finally, we're going to take a look at Unite Body functionality, which is not new, but we're going to take a look at how it can improve your ability to quickly and efficiently get to the results. So the first topic, as I said, would be assembly body mesh. In the SolidEdge 2022, body mesh was only available in part environment. With the SolidEdge 2023, now we offer body mesh that supports assembly and sheet metal environment. That's very important because a lot of customers using SolidEdge simulation for assembly analysis as well as sheet metal. In SolidEdge 2023, the mesh dialog is modified, as you can see on the right-hand side, and it allows for that option to be selected, body mesh. I'd like to mention also that this new option not only allows you to use this automatic tool, but also it will improve your chances of successfully meshing the part, as well as improving the mesh quality automatically. The algorithm behind this functionality allows you to do that and allows you to create more efficient and more accurate mesh. So there are some parameters available. As in previous version, including SolidEdge 2022, some parameters were hard-coded. Now in SolidEdge 2023, some important parameters are available for users to select. What it accomplishes, it allows users to control body mesh for better mesh quality, and the options are available only when body mesh checkbox is selected. Just to name a few, you can see that points around circle, that's important characteristics. You can automatically define how many elements in your mesh are going to be placed on the cylindrical surfaces. As you can see in the image on the left side, there is much improved mesh on the hole, on opening. Minimum element size factor. It has to do with mesh refinement. So when element forces refinement of the mesh go too low or too fine, then this value can be specified. The range is between 1 and 100. Another parameter is growth factor. This control determines the maximum rate at which face edges vary from one face to another. It's very important parameters because if you want to control your mesh tightly, this is where you can control it. And the recommended range usually from 10 to 60%. Another element is maximum points around circle. Specifies the maximum number of points around complete circle. The valid range is from 4 to 128, and so on. So let's explore body mesh option. As I mentioned, it's available on assembly now as well. We have this helicopter internal configuration. We're going to focus on the landing gear today. And what I'm going to do, I'm not going to solve it, of course, because it's going to take some time, but we're going to see how body mesh will improve chances of accurately and efficiently mesh this subassembly. So we're going to select all the components, and all I have to do just select mesh. We'll select default and try to mesh. I'm going to speed up this process so we don't waste your time. So as you can see, system came back with an error. It couldn't accurately mesh this particular part. Solid offers to run geometry inspector. Let's do just that. We can select occurrences. Let's say this occurrence, and let's see if we have any faults. And of course, we don't have any faults. It's just matter of more complex geometry than we anticipated. And of course, if we zoom in, you'll see we have all these additional small faces, and maybe that's what's causing the problem to mesh that part. But body mesh comes to rescue. So when we try to mesh it second time, we select this option body mesh, and let's, with the same setting for subjective mesh slider, let's go and try to mesh it now. And of course, you can see that now it meshed this landing gear successfully. So this is a great help when you're trying to analyze your design and you don't want to deal with little inconsistencies that you might discover. And instead of trying to clean up your parts, you can easily use that option body mesh and successfully mesh what otherwise might give you a problem. Next up would be reusing existing mesh. So it's very important to be able to avoid extra work, of course, to do it in the most efficient way to get to your results. And this is exactly what inside Edge 2023 now is offered. So mesh gets copied during the copy or creating a duplicate study. Support is available in part, assembly, and sheet metal environment. So let's go and open that reuse mesh part. First, of course, we need to create study. Let's go and create new simulation. Geometry is going to be defined automatically. As you can see, we have only one single part. So let's go and define some boundary conditions. First, we're going to fix this. Conveniently, I can use feature instead of selecting individual faces. And we're going to apply load. I'm going to select this flat surface. And we're pretty much ready to mesh and solve. It's going to go really quick because it's a simple part. We can take a look at animation. And as you can see, because of the force applied horizontally, it goes and deflects in the horizontal movement. Let's duplicate study. We can just right click and say duplicate study. And here's this new dialog box that comes up and asks us if you want to mesh to be copied with your study. And of course, we want that. We don't want to remesh it or do anything with that mesh. The only thing is that I want to change here is direction of the force. Maybe I want to have it at 45-degree angle. And let's solve it again. And as you can see now, it actually, if we animate it, you can see that now handle kind of moves downwards as well as in the horizontal orientation. So here is your reuse mesh option. Very convenient, very efficient way of reusing mesh instead of remeshing and waiting till it happens. Mesh quality check. It's very important to understand how good or bad your mesh is because quality of mesh greatly affects your results, and it's very important to understand where you're lacking in quality. So this is a new option available inside Edge 2023. There is option which is called check element quality, And after you mesh the part, you can go and check for at least 14 Nastran quality checks. You can select only error, or you can select warning and error type of warnings, type of quality check. Results shown in Notepad after you run this command, and you can easily and efficiently evaluate the quality of your mesh. There are quite a few parameters that can be tweaked and adjusted to what you're actually checking against. First one is skew parameter. It evaluates and measures different angles, whether it's triangular mesh or quadrilateral mesh. It measures angles and checks for deviation from default values. Another parameter, aspect ratio, based on the ratio of the length of the longest element edge to the length of the shortest edge. Again, it checks for consistency of elements. And finally, maximum internal angle. It evaluates whether the included angle at the corners of elements deviate from the optimum condition. All these parameters are useful and can be checked against. So let's go and open this part. This is sheet metal part that we extracted already mid surfaces from. So I'm gonna just leave only mid surface. And let's go and create new study. And you know that Solid Edge is smart enough to know that we need surface type of mesh automatically because we are using extracted mid surface. And of course, thickness is automatically extracted from the part and material. All this information happens automatically. I'm not going to solve it. I'm going to focus on mesh only. So we're going to go and mesh this part using defaults. And here's this new check element quality functionality where you can define error or you can define warning and errors. And based on your selection, it gives you different set of characteristics to check against. A lot of this information is set by default to most meaningful information, but you can change every one of those. Aspect ratio, minimum internal angle of the mesh element, and so on. So all you have to do, just click show elements, and the system comes back and presents in a textual file. It presents how many elements failed, and we can visually, of course, see those failed elements. You can see they're displayed in red, warning displayed in yellow. They color coded. We have 10 errors in this particular mesh. Let's go and try this again. This time we're going to change mesh to make it smaller. Let's go significantly smaller. And when we run this check element again, you can see that we have still 4 errors in this mesh. So if I want to eliminate error completely, the system suggests that mesh quality can be improved by using body mesh or create a finer mesh. So let's try to do that. I'm going to go and add body size and specify it as 5 millimeters for the whole body. Let's go and mesh it again. And let's check the quality of mesh now. And now we have 0 errors. So this is how you can eliminate your errors by checking different options, either removing, making mesh finer or adding specific elements like surface mesh, body mesh, and so on. This is just an example, but let's take a look at a more meaningful example. If you remember, we meshed this landing gear. Let's go and see how well we did with the mesh here. Let's go back and check element quality here. We're going to say warning and errors, of course, and we're going to say show elements. It might take a little bit longer because, of course, it's much more complex mesh. We have much more complex geometry here. Again, I'm going to speed it up and come back when it's done. And as you can see, we have 432 errors here. So let's examine where we have errors. If you look at these cross members, you can see that we pretty much have zero warnings or errors. Most of them are on this landing pipes or landing gear itself. So this gives us indication where we need to focus our efforts to improve mesh. So what we can do, as I said before, we can go and apply body size, focusing only on these two elements of landing gear. And let's go and mesh it again. Okay, we meshed successfully because we're using body mesh option. So let's go and check our quality again. And now we can see that we have zero failed elements. So we can have zero warnings, zero errors. So this is the tool that you need to use in order to improve the quality of your mesh. And this tool actually is a very good indicator of where you need to focus your efforts to improve mesh. Next step would be unite bodies functionality. This is a very powerful way of, again, quickly and efficiently get to final results instead of dealing with intricacies of setting up study. The important part is that Unite Bodies functionality can be used in assembly, part, and sheet metal environments. So what happens, it creates single body that consists of sheet metal construction bodies or combination of solids and sheet bodies. So it's usually applicable when components are welded together or somehow rigidly connected, and it makes sense to use this. And very important distinction. If you remember in the previous section, Solid Gems, we looked at union command. This is different because with union command, you are uh, connecting, or I should say, glue together parts of the same material. Here you have ability to define unique thickness and material to each element of your unit body. So let's take a look at how it works. So I need to analyze this frame, and as you can see, it consists of some frame members as well as some sheet metal members. So in order for us to successfully accomplish this task, as you know, the thickness over length for sheet metal parts is really great, that ratio. And we need to extract mid surfaces. Solid simulation offers excellent functionality for that. We can extract mid surfaces even on assembler level. We don't need to go and do any of that on a part level. And we're gonna extract those two members and one mid member. So we can successfully hide the hide these members and leave only extracted mid surfaces. And let's go and start simulation. So first I'm gonna go and create simulation the way we normally would do. Create new study. And in this case, we're gonna select mixed type of mesh because we have a mix of solid bodies and extracted mid surfaces. And I'm gonna select all these documents at once. So before we even start applying loads and constraints, we want to go and create connectors. And connectors are going to be somewhat involved because, again, we are dealing with several members. Let's go and create connectors and try to create automatic connectors between all the components. When we examine the connectors we just placed, conveniently Solid allows you to go through using arrows on your keyboard, and we can quickly see that we created pretty much all connectors, and we can accept, of course. We created all connectors, but connectors between this member and the two frame members, solid members. So let's go and do that manually. So as I promised you, you would have to go and create some connectors manually. We're going to connect edges of this member with faces of that solid member. And we're going to repeat the same thing with the other side. Okay, now that we've accomplished that, we can go and create some constraint loads. We're going to hold this frame from the bottom, the load. The load is going to be placed on these faces, these two faces. So that provides a really convenient way of changing orientation and just with one button click. And we're going to apply some load. So let's go mesh and solve. Let's increase the mesh size, maybe something like that. I'm going to shorten this processing time in the video because it takes some time, so I don't want to waste your time. So when the results pop in, I'll show you the results. Okay, and now we can see that we finished analyzing the frame, and the stress is about 7.5 KSI for this frame. But now let's examine the other way. How would we deal with this frame? So solid simulation provides really a powerful way to connect geometry. It's called unite bodies, and it's different from union that we discussed earlier in the gems, solid gems session, because unite bodies allow you to assign unique materials and thickness to different members. As a union just connects together existing parts. For that, it needs to be same material. We're gonna select all members. And as you can see, successfully created that unite body. Let's go and hide the members. Okay, now that we've hidden all the members of the assembly, let's go and create new study. And in this case, again, I'm gonna go with mixed and general bodies because this will allow me to select that unite body. And as I mentioned, we have ability to assign different properties to different parts of this assembly. So I'm gonna go and easily accomplish that task. Override properties, that's what we're looking for. And maybe we can assign different material and different thickness. to all the members that we're interested in. And for this one would be slightly different. So we have to go and repeat this procedure. It's going to be the same material, except it's going to be slightly different thickness. And we can do that with a window. We don't have to select one by one. So as you can see, now we have these override properties with appropriate material and thickness. So this is what's different from that union command that we discussed earlier in SolidEdge jam session. Now that we've done that, we don't have to deal with any connectors between the members. All we have to do is just define the load, same way that we did previously. And we can even borrow the constraints from previous study. You can copy and paste it here. We're pretty much done. So you can see how easy it is to use unite bodies instead of trying to set up all the connectors like we did in previous study. So let's go and analyze. We're gonna set up mesh the same way like we did before. Hit mesh and solve. And again, I'm gonna speed up this processing time so I don't waste your time. And we're gonna arrive at the results pretty quickly. Now that we got the results back, as you can see, if we compare results, we are pretty close. So here's the advantage of having Unite bodies functionality available inside of SolidEdge. You avoid extra work applying connectors, and setting up the study goes much smoother. Thank you for your time. If you have any questions or comments, or you need to reach out to me, here's my contact information. Good afternoon. Welcome to SolidEdge Simulation Hidden Gem session. Today we're going to take a look at a couple features that maybe not so much common. First, we're going to take a look at convergent model simulation. That's a very important topic because in today's marketplace, more and more companies are taking advantage of 3D printing technologies, and that's exactly what we're going to be talking about today, the models suitable for 3D printing. And the second topic we're going to cover is tip over analysis, goal seek, and motion analysis. We're going to take a look at furniture analysis today, but it's applicable to pretty much any designs that are prone to tipping over. With SolidEdge simulation, you can easily incorporate mesh-based geometries into design. What's important to understand that simulation studies can be performed on convergent models. Those convergent models usually created using generative design or some other sources. We're going to talk today about generative design produced models. Simulation on convergent models is supported in part environment, and it's highly accurate because it's based on SimCenter Nastran solver, which is de facto industry standard, and it's part of accelerator portfolio of Siemens products. So what is convergent modeling and why is it called convergent? The modeling capabilities in SolidEdge software represented by a set of different integrated tools that work really well with mesh bodies. We are using term hybrid models. A hybrid model capabilities allow BREP geometry coexist with mesh geometries. The difference is that BREP geometry is geometry that usually produced by a regular CAD tool. And mesh geometries are usually having different sources, like generative design or maybe scanned data from outside and so on. So using convergent modeling, engineers can send any mesh bodies pretty much directly to additive manufacturing, to 3D printing, or for analysis. At the same time, using hybrid approach, working on hybrid models, they can continue modifying their designs within Solid Edge. The feature pretty much allows users to simulate convergent models in the Solid Edge simulation, and it's a huge leap forward. There are three different types of convergent models. They include generative design optimized model, converted mesh model, and STL model from outside world. The use of generative design model is as follows. Once you generated that model, you would have to detach it from study in order to perform simulation on it. Then in Pathfinder, under construction bodies, that's where body detached from study would be residing. You can right click on that and toggle it to design body and make it active. At this point, it can be used in the simulation study. So let's explore new simulation capabilities in Solid Edge 2023 in conjunction with generative design approach. So we have this bracket that the goal here is to lower the weight of this bracket. So we're going to start with generative design, and as you know, generative design works as follows. We define the study, and then we define the part that we want to process and arrive at most efficient design, and system will do all the heavy lifting. So first we're going to define the fixed constraints. It's pretty much similar to simulation, and we can do that either by phase or by feature. It's quite efficient way of defining constraints. So we can select features, and we select feature like mirror. While we're defining the constraints, we can define the offset as well. And conveniently, we can encompass the outside edges, outside rounds of this part. Then we're going to go and apply force. It's quite easy to do as well. We can define it by feature, by phase. Solid Edge is very consistent in this matter, and we can define it as along the vector, normal to face. In this case, I want to use our steering wheel tool to define the direction, and we're going to give it like 200 pounds value for the load, and for the offset we're going to define the value as well. So we're pretty much done. One thing which is really useful in the generative design is defining plane symmetry. So even if you have non-symmetrical load, system will try to do its best to arrive at symmetrical configuration of your part. So we're going to define that plane as a symmetry plane, and we can take a look at the generative design navigator, and you can see we have now planar symmetry defined. Okay, we can hide now all our constraints and the loads, and we can go and proceed to generating the part. I'm going to go and apply quite aggressive material removal algorithm and click generate. So system will take in account all the defined boundary conditions, loads, symmetry, and all of the above, and will arrive at the most efficient design, of course. One thing you need to be aware that we're talking about here hybrid modeling, which means we combine mesh bodies with B-wrap type of geometry, which is usually developed when you use your CAD modeler. It gives us really great flexibility because afterwards we can clean up the model, we can adjust geometry as we go, and that allows us to actually work with the final result, with that organically shaped body. Now the system finished processing, you can see that we arrived at the solution, but a couple of things I would like to change here. First of all, I don't like this gap up front, not a problem. Let me go and show our original body, and we can add additional constraint, which is available in Solid Edge 2023 generative design, which is called maximum displacement. So I can pick specific face, define the location approximately, and we have ability to define whether it goes in a specific direction, or we're going to select absolute magnitude. And once we define that constraint, we'll go and regenerate the body. So you'll see that after we go through this process that the final result is going to look quite different. That front wall is going to be preserved based on our maximum displacement, new type of configuration for this study. And also I did mention that before, we have some manufacturing settings available where you can define specifically configuration for regular machining, subtractive machining, because this model actually lends itself very well to 3D printing. But if you're willing to go with traditional manufacturing, there are some special settings that will allow you to control how material is generated and added to the model based on our final result. But again, in this case, we're looking at the final result for 3D printing, where you can easily define material and send for 3D printing or use any in-house 3D printer available. It's a quite fast process. So now you can see we have this front wall added. We have ability to actually clean up this model, as I mentioned earlier. Conveniently, SolidEdge provides tools for very efficient way of dealing with this. We can just clean up this face and avoid that little step up front. So conveniently, of course, we can take a look at stresses after we generated this final body. And you can see that our model actually reaches certain stress, and you can see the stress concentrators. But what if we want more accurate analysis? And what if we want to go through what-if scenarios? So for that, we can use SolidEdge simulation. Quite easily, we can just detach this body from our study and go and start our analysis. But before we do that, so right now we're looking at construction body. I can easily move it to design space and also make it active body, which means this is the one we're going to be analyzing when we create a study. So let's go and create new study. And you can see how conveniently I can switch between different tabs. Here I was in the generative design navigator, now I'm already in simulation navigator. It's all one single integrated environment. This is the most important thing. So of course we're going to select this body to analyze. Material is of course inherited. And let's go and apply some constraints. We're going to pretty much apply the same constraints as we did in generative design study. So we're going to add constraints to these 4 holes. This is how we're going to hold this bracket. And as far as loads, again, same type of load we're going to apply to these internal faces. And of course, we're going to use a lone vector type of constraint. Same load as before. And we can mesh and solve this model. Let's go and do just that. You could see it's quite easy to set up this study using this hybrid model. As I mentioned, we combine mesh body with B-rep type of geometry in this model. And what's really powerful now in SolidEdge 2023, we do not have to create special analytical surfaces like before. And you can see the model is not properly meshed. There are some problems with the geometry. Maybe we can go and analyze, but you can see there are no problems with geometry. So we're facing the same situation as we dealt with in the previous sessions. So what we can do, we can go and select that body mesh. Body mesh not only creates cleaner, more efficient mesh, but also it eliminates some discrepancies, some sliver faces in a way that algorithm really very powerful. Now we're going to be able to solve this model and mesh it automatically in one single step. So this body mesh, we talked about this before, it's a really powerful way of arriving at the results really quickly than trying to clean up the geometry. So results are almost there. And as you can see, we have now results that we can actually analyze. We can take a look at the different aspects of our model. So we can animate these results. We can take a look at stress. We can take a look at displacement, not only stresses, but all this data we can create a report. So again, the beauty of this approach is that we can take results of generative design and use them in solid simulation. It's a one single integrated environment, and no longer you have to go and specifically add additional BRAP geometry to be able to analyze this body. The next topic would be tip over goal seek and motion analysis. So what is goal seek? Let's first cover the tools available. Goal seek, it's automated engineering calculations that are available in SolidEdge for quite some time. It operates on the 2D data as well as on the 3D geometry. The way it works, it finds a specific value which depends on another variable, for example, or formula. And by adjusting the value of that variable, the system will arrive at the most efficient design. You can use goal seeking to find the best solution of multiple what-if problems, and it works with 2D data as well as with 3D data. It can be used, for instance, to update physical property of a design body or the whole assembly, and that's what we're going to take a look at today. Another tool we're going to be using today is motion analysis. SolidEdge motion simulation capabilities allow users to perform functional performance analysis of their design when moving components are involved. SolidEdge motion supports quite sophisticated designs, and the resultant output from those studies is results such as velocity, acceleration, reaction forces. The data can be extracted into Excel for further analysis, and most important, can be extracted into SolidEdge structural analysis. The solution supports multiple elements such as springs, dampers, general forces, and moments. So why tip-over analysis? The Consumer Product Safety Commission came up with a mandatory furniture tip-over standard that was published in Federal Register. The rule goes in effect in 180 days since publication, which means until May 24th, furniture manufacturers have to make sure that their products meet the standard. The rule applies to pretty much every freestanding chest, dresser, armories, bureaus, and so on. And any storage furniture that is 27 inches or more in height fall into the scope of this standard. So that's why furniture manufacturers are really concerned about this, and they're looking for solutions to test their designs beforehand and come up with appropriate solution to meet the standard. So let's take a look at how SolidEdge simulation tools can help manufacturers meet these new requirements for furniture tipping over. It can be applied not necessarily to furniture only, but in this example, we're going to take a look at this dresser and how we can test it using multiple simulation tools available in SolidEdge. First tool would be goal seek. Under inspect, you will see this goal seek, and we're going to use it to virtually test this dresser. But before we start doing that, let's go and explore at which point it might start tipping over. If we go to variables, you can see that all drawers dependent on the first drawer. So let's go and extend that to maximum. So all drawers would be extended to in a maximum position. If we go into unshaded mode, you can see that we're pretty much almost at the final step before the drawers start falling out. Under inspect properties, you'll find mass for the whole assembly. Very useful information, and also you can display symbol for center of mass. If anything changes, components are removed, added, you can hit update button. It will update the mass for the whole assembly. So now if we take a look at this assembly, you can see that center of mass, that green dot, is slightly to the right along y-axis. The dresser will start tipping over when that center of mass would be to the left of 000 point along y-axis. And it's going to be balanced if that green dot is exactly above 000 point along z-axis. Under inspect, we have goal seek that allow us to calculate many different things: momentum, inertia, mass, a lot of different things, but in this case we're interested in position of center of mass along y-axis, and we're going to be solving against variable first drawer, which controls position of all drawers. So we want to find out at which point we reach 0. If I hit accept, System will go and calculate position of all drawers. And as you can see, they can be completely pulled out before dresser starts tipping over, even this unrealistic situation where they completely pulled out. This is good information, but what if somebody is leaning on this dresser? To test for that, we need to add additional load on the top drawer. We have a weight already part of the assembly, and additional tip, right now weight was inactive, and how did I inactivate it? Under occurrence properties, we can check off many different things, whether this part would be part of the drawing, bill of material, if it's going to part of interference check. But in this case, I'm using physical properties. If I turn them on, say yes, then this weight is going to be part of the equation now. So let's go and repeat our goal seek as weight is changed. And when we start iterations, you'll see that now position of the drawers changed because that weight is taken in account. So let's go into unshaded mode and we can see the position of those drawers in relationship to the dresser. Let's place dimension to measure the distance between the axis around which unit is going to tip over and the top point of the dresser, or top drawer, I should say. Here's our distance, and with this situation, with this weight, this is how far drawers can be pulled out, and if they pulled out a little bit more, the unit will start tipping over. We also have counterweight here. What if we want to increase that counterweight? We can use the same tool and under inspect, goal seek. For this particular case, we want to estimate the mass. So let's go and change it to 80 pounds of mass. And we're going to control the extrusion variable that controls the size of this component. It comes back and it shows us that now we have 80 pounds of mass for counterweight. Let's see how we can calculate the weight required for this unit to tip over with a new counterweight. For that, we're going to go back to variables and change the position of all drawers to 20 inches like we did originally. But because we increased counterweight mass, we can now estimate what mass is required for the load for the unit to start tipping over. For that, we're going to go and copy this dummy variable link. I just created a variable called load, and we can efficiently copy this and paste it into variables for the weight. Paste that link. So what now we can do with this, if we go to goal seek and start analyzing our unit, we can solve against load. So this way, system will calculate how big of a load is required to counterbalance that weight of the dresser and the counterweight in the back. So let's take a look at the value. We're talking about 71 pounds of mass that is required for the unit to start tipping over, actually over 71. This is the first method that we can use to figure out approximately the load at which unit will start tipping over. I will present you a different method using motion analysis. As you know, Sadech includes now full motion capabilities. So let's go and hide the weight right now, because in motion we're going to use slightly different method to apply load. And under tools, environments, you'll see motion environment and unit. When we start creating our mechanism, motion is tightly integrated with Sadech. It will take all the parts and try to position them into moving parts or ground parts. In this case, when I exclude weight, but the rest of them is okay. So what happens, it puts weight in assembly components. It's now not part of any moving parts or ground parts. And you can see based on assembly relationship, motion created whole bunch of different joints. If we simulate this mechanism, you'll see that units simply fall through based on gravity. So we need to add additional joints to control the tipping over. We're going to define additional joint, and we're going to position it at this location and define the direction. And if we look closely, you can see that direction of that new joint is towards the front. So the unit will be tipping over forward. So let's go and solve this. You can see that based on the counterweight and the weight of the dresser itself, the unit is tipping over backwards. I told you earlier that we're going to use different method of applying load instead of weight. So now we can apply different action forces. So we're going to apply force to the top drawer somewhere in this area, and direction is defined by the top panel. All we have to do is just change the direction, so we apply load downwards. And let's add the same 70 pounds of force that we had previously. And you can see it's still tipping over backwards. And we could try guessing different values, but what if we need to calculate the range of values that is within tipping over? For that, you can just use the expression. Under function, we can change it from constant value, can change to the expression. We define the expression as follows. So what it tells us that if a marker, we're going to talk in a second what marker is, if a marker for that specific force is exceeding 1 degree per second angular velocity, then the amount of force would be 1000 multiplied by time from the beginning of the animation. If that speed is not reaching 1, then it's going to be 0 pound of force. Every joint, every applied constraint has its own marker. So we can go to the list of those markers and find specific marker. It's 330. And all we have to do is just say OK, and it will replace marker appropriately. So if we animate it now, you can see that the unit is tipping over forward instead of backwards. And what it tells us that expression is working. So it's solving. And we can plot a couple different things. First of all, we're interested in the reaction force. As you can see, the reaction force increasing until it dropped when the unit reached certain velocity. Then also for the top member, which is the most remote member of the assembly from axis of revolution, axis of tipping over, we can plot for this component angular velocity. And of course, we can conveniently position unit just using this slider and reach the point where we can estimate. You can see that marker right here, it's moving up and down, giving us approximate value for the reaction force. So if I position it here somewhere, we're talking about exactly 70 to 80 to 85 range of force. So let's go back and define the force as a, instead of expression, constant value. Let's go and give it 75, value of 75. And now you can see it's tipping forward. We can fine tune it to be exact. Let's do 73. And if you look closely, you can't even tell if it's tipping forward or backward. But with the dimension, this is our indicator. Let's take a look at this in initial position and then in the tipping over position. Because it got smaller it means that the unit is still tipping backwards. In order for it to indicate tipping forward, it needs to be increasing. So let's go and increase our force once again, make it 74. Now we're moving forward, so it's somewhere between 73 and 74. As you can see, this indicator dimension increases. So right now it's initial position, and then tipping over position, it's increasing its value. So this is how you can use simulation tools inside of Solid Edge to determine the critical point at which your design will start tipping over. And this is very useful. It can be applied, again, not only to furniture, but pretty much any design you're concerned about. It actually helps you do this testing virtually instead of doing real physical prototyping. Of course, it doesn't replace it, but still, it's a great help. It reduces greatly the number of physical prototypes required. Thank you for your time today. If you have any questions or comments, you can contact me at this email address.